The James Webb Telescope has just discovered something massive hiding on the edge of the observable universe. We see examples of bubbles and cavities, along with hundreds of new stars that we've never seen before. When you look up at the sky on a clear night, you'll likely see a multitude of stars, and it's incredible that some of them are trillions of miles away. But scientists are excited about something even further away, thanks to the new James Webb Space Telescope. They've found something massive lurking at the very edge of the universe. What have scientists discovered? How did the JWST assist in discovering it, and can the object have any effect on our planet? Join us as we dive into the massive object that the James Webb Space Telescope has just discovered hiding on the edge of the universe. As we look at the image, we see not just galaxies but a cluster, revealing so much detail in a way we've never seen before. Imagine wanting to complete a task but not having the proper tools, like trying to geek out on your smartphone but lacking the precision tools to crack it open. Scientists were once in a similar position, until the launch of the James Webb Space Telescope. The universe contains countless mysteries, and one of the most puzzling is the question of how it all began. There are many hypotheses, but they need to be proven. The proof centers on one thing: finding out exactly what happened at the beginning of the universe. Was the universe always there, always expanding? Solving these mysteries requires the best equipment humanity has ever made, tools capable of seeing the edge of the universe and studying some of the oldest formations in existence, many of which are billions of years old. This is where the JWST comes in. The JWST is the most powerful telescope humans have ever conceived. Galileo Galilei, the father of the telescope, would be proud of how far his invention has come. However, progress comes at a steep price, $1 billion, and many anxious moments during its launch. Now that everything has gone smoothly and the JWST is in its permanent orbit, NASA can sit back and enjoy the scientific bounty from this massive space observatory. One of the most exciting things about this telescope is that it allows us to see the very first galaxies born in the early universe. Even in its short operational time, the JWST has already revealed shocking things about our universe, many that scientists didn't see coming. At this rate, it's no exaggeration to say that the JWST will challenge everything we thought we knew about the cosmos. The JWST is already taking us far back into the past, nearer to the edge of the universe, offering scientists a glimpse of the early universe. We must seize this opportunity before humanity faces an unforeseen disaster that we cannot anticipate or control. The JWST's ability to detect faint light from incredibly distant galaxies, glowing in infrared light invisible to the human eye, is helping astronomers better understand how galaxies formed and evolved in the early days of the universe. The image capturing scientists' attention shows a galaxy cluster, MAX 0647, along with the distant galaxy MAX 0647 JD. This cluster appears as a dazzling group of galaxies, shining like gems against the dark backdrop of space. The distant galaxy is visible thanks to a phenomenon known as gravitational lensing, where galaxies in the foreground act like magnifying glasses, allowing us to see objects far behind them. The discovery of MAX 0647 JD is significant. While it was discovered 10 years ago using the Hubble Space Telescope, the JWST quickly revealed something surprising about the cluster: two distinct features. Scientists are unsure whether these two objects are separate galaxies or two clumps of stars within a single galaxy. They are counting on the JWST to provide the answer. These aren't even the most distant objects the JWST has found. That honor goes to one of the earliest galaxies, captured about 350 million years after the Big Bang. This galaxy, called Glass Z12, along with another formed about 450 million years after the Big Bang, was discovered shortly after the JWST began its infrared observations. Before this, the earliest galaxy observed was GN Z11, which existed 400 million years after the Big Bang and was spotted by the Hubble in 2016. The JWST's ability to capture distant galaxies has revealed that the universe was producing galaxies much faster and earlier than scientists initially thought. In just a few hundred million years after the Big Bang, there were already numerous galaxies. Both Glass Z12 and the other newly discovered galaxy have spherical or disc-like shapes but are much smaller than the Milky Way. Though distant, these galaxies are extremely bright and generate stars at a rapid pace. Further research suggests that galaxies may have begun forming just 100 million years after the Big Bang, a timeline that challenges current theories about how and when the first galaxies appeared. The early universe was undeniably chaotic, yet the structure of these two galaxies turned out to be surprisingly calm and orderly. Another thing that has baffled scientists is the sheer brightness of these galaxies. One possibility is that these galaxies were massive and contained a lot of low-mass stars, similar to galaxies formed later in the universe. Another possibility is the opposite, smaller galaxies with fewer, but extremely bright stars. These luminous objects, known as population 3 stars, are theorized to be the first stars ever born in the cosmos. These early stars were thought to be blazing hot and comprised of hydrogen and helium. The stars that followed contained heavier elements created when the first stars exploded. So far, no population 3 stars have been found in our local universe, but scientists are hopeful that the JWST, with its ability to peer deep into the cosmos, may one day spot them. It wouldn't be surprising if the older of the two galaxies, Glass, Z12, contains these elusive stars. The JWST continues to break records, and it has done so in an incredibly short time. While the distant galaxies Glass, Z12 and MAX 0647JD are awe-inspiring, there's even more. Scientists have identified another galaxy candidate, Sears 93316, which formed about 250 million years after the Big Bang, setting a record with a redshift of Z16.7. This discovery pushes the boundaries of what we thought we knew, and there's no telling what else the JWST will uncover as it continues to gaze deeper into the universe. This discovery is a massive deal, demonstrating the power of the beast developed and launched by NASA. SEERS means Cosmic Evolution Early Release Science Survey, a special program meant for imaging with JWST. Researchers will confirm the redshift with follow-up observations using spectroscopy. This is why they still refer to it as a galaxy candidate. However, the study has already determined that Sears 93316 can't be a low-mass star or an unobstructed active galactic nucleus. This conclusion is based on imaging data from NIRCam, JWST's primary imager. After the Big Bang took place, the universe entered what is known as the Dark Ages. This was the time before any of the stars we see today were born. However, the observations of this galaxy push back our understanding to a time when scientists believed the first galaxies ever to exist were forming. NASA says the JWST can detect galaxies at redshifts greater than 20, which correspond to less than 200 million years after the Big Bang. However, these galaxies are likely extremely hard to find. With the detection of Sears 93316, scientists hope that they may exist. If you've been baffled by redshift and shifted light, here's what they mean. Following the Big Bang, the universe was like a hot soup of particles, protons, neutrons, and electrons. As the universe began to cool, protons and neutrons combined into ionized atoms of hydrogen and some helium. In this ionized form, the atoms of hydrogen and helium attracted electrons, turning them into neutral atoms. This allowed light to travel freely for the first time in the universe, as the light no longer scattered off free electrons. This was a turning point in the universe, as it was no longer opaque. But it would still take some time, perhaps a few 100 million years after the Big Bang, before the first sources of light would begin to form, bringing an end to the cosmic dark ages. This is quite interesting, as it means the universe was ready to transmit light before the sources of light were even formed. So what did the universe's first light, the stars that fused existing hydrogen atoms into more helium, look like? We don't know yet. When exactly did these first stars form? We don't know that yet either. These are the questions scientists are waiting for JWST to answer. Now, what about shifted light? Imagine light leaving the first stars and galaxies nearly 13.6 billion years ago and traveling through space and time to reach our telescopes. What this means is that we are seeing these objects as they were when the light first left them 13.6 billion years ago. By the time this light reaches us, its color or wavelength has shifted towards the red, something called a redshift. In the case of very distant objects, Einstein's general relativity applies. It states that because the universe is expanding, the space between objects is stretching, causing them to move away from each other. Moreover, any light in that space will also stretch, and the light's wavelength will shift to longer wavelengths. This can make distant objects appear dim or invisible at visible wavelengths, because the light reaches us as infrared light. When we refer to redshift, it means that the light emitted by these first stars and galaxies as visible or ultraviolet light has been shifted to redder wavelengths by the time we see it from Earth. For very high redshifts, objects furthest from us, visible light is generally shifted into the near and mid-infrared parts of the electromagnetic spectrum. Therefore, to observe the first stars and galaxies, we need a powerful near and mid-infrared telescope, which is exactly what Webb provides. Another distant object that the JWST has captured in remarkable detail is the Pillars of Creation, first photographed by Hubble in 1995. While impressive at the time, JWST's image of the pillars is far superior. These three-dimensional pillars resemble rock formations but are made of cool interstellar gas and dust, appearing semi-transparent in near-infrared light. Thanks to the images taken in 1995 and 2014, JWST's new image of the Pillars of Creation will help researchers improve their models of how stars form by providing more precise counts of newly formed stars and the quantities of gas and dust in the region. Over time, scientists will gain a clearer understanding of how stars form and burst out of these dusty clouds over millions of years. When the JWST took another image of the Pillars of Creation using the mid-infrared instrument, MIRI, the result was somber and chilling. Another image captured by JWST showed the nebula 30 Doradus, known as the Tarantula Nebula, in great detail. It is one of the largest and brightest star-forming regions in the galaxies nearest to our Milky Way. The Tarantula Nebula is located 161,000 light-years away in the Large Magellanic Cloud galaxy, named after its long, dusty filaments resembling a spider's legs in older images. The image shows the stellar nursery in unparalleled clarity, revealing tens of thousands of young stars that were previously shrouded in cosmic dust and unseen before. For many people, the most memorable feature of JWST is its size. JWST is the largest space observatory ever built, with a sunshield base measuring a massive 22 meters by 12 meters, about the size of a tennis court. Despite being nearly twice as large as Hubble, which is 13 meters long, JWST weighs only 6,500 kilograms, almost half the weight of Hubble. JWST's gold-plated mirrors have a total diameter of 6.5 meters, much larger than Hubble's 2.4-meter mirror. This gives JWST an approximately 15 times wider field of view than Hubble. Although both telescopes are iconic, they function differently. Hubble's primary focus is on visible and ultraviolet light, with some infrared capability, but nowhere near the extent to which JWST can observe. JWST is designed specifically to work in the infrared spectrum, meaning it can't observe in ultraviolet light like Hubble, but it can focus on bright, distant galaxies. JWST's ability to observe objects over 13.6 billion light-years away allows us to look back 13.6 billion years, bringing us close to 100 to 250 million years after the Big Bang. Most of JWST's size is due to its large sunshield, which was designed to unfold during launch because of space limitations on the launch vehicle. The sunshield is crucial for JWST's infrared cameras, as without it, the telescope would risk blinding itself to the lights of the objects it is trying to observe. One key difference between the two telescopes is their distance from Earth. Hubble orbited above Earth's atmosphere but was close enough to be serviced for repairs. However, JWST is located 1.5 million kilometers away, far beyond any human reach, meaning no one can repair it if something goes wrong. One of the fascinating discoveries at the very edge of the universe is a galaxy named AEL 2744Y1. This galaxy is special for many reasons, including its extreme distance from Earth. Light from AEL 2744Y1 reaches us after 13 billion years of travel, making it one of the most distant objects known. The universe is estimated to be 13.8 billion years old, meaning we see AEL 2744Y1 as it was when it was only 650 million years old. This is true for all distant objects in space, as the light from them takes so long to reach us. AEL 2744Y1 was discovered using 3 telescopes, Spitzer, Chandra, and Hubble. Hubble captures images in visible and near-infrared light, while Spitzer observes in the infrared part of the electromagnetic spectrum. Scientists use Chandra to collect additional data using X-ray wavelengths. By combining the data from these three telescopes, astronomers were able to observe galaxies up to 100 times farther than any one telescope could have done on its own. The astronomers attached to the Institut de Astrofísica de Canarias, IAC, and La Laguna University in Spain began their observations with the Hubble Space Telescope, which first detected the galaxy in question. This was followed by the use of the Spitzer telescope, whose instruments help calculate the object's distance and location. Additionally, the telescope was used to determine how many stars were in the galaxy. The scientists employed a method known as gravitational lensing when they photographed AEL 2744Y1. The underlying principle is similar to how a magnifying glass bends sunlight, as images from distant galaxies are brought into focus by galaxies closer to Earth. This natural telescope, which allows us to view the most distant objects in the universe, was first predicted by Albert Einstein in his general theory of relativity. How large is this galaxy? Astronomers have determined that AEL 2744Y1 is quite small in size, being about 50 times smaller than our Milky Way galaxy, measuring around 2,300 light-years in width. However, despite its small size, it makes up for it with an impressive rate of star production, generating stars at a rate 10 times faster than the Milky Way. This is typical of galaxies in the young universe. AEL 2744Y1 has a redshift of 8. Redshift is a way of measuring the degree to which an object's light has shifted to redder wavelengths due to the expansion of the universe. In comparison, the furthest confirmed galaxy before the discovery of AEL 2744Y1 had a redshift of more than 8. Some may say the universe is 46.1 billion light-years in diameter, but that is merely the limit of the observable universe. There is much more beyond what we can see. How do we know what lies beyond the observable universe? We can make inferences based on the laws of physics and by measuring what we can within the observable universe. For instance, we observe that the universe is spatially flat on the largest scales, with a curvature precision of 0.25%. If our current laws of physics are accurate, we can set limits on how large the universe must be before it curves back on itself. Observations from the Sloan Digital Sky Survey and the Planck satellite suggest that, if the universe does curve back in on itself, the observable part is so indistinguishable from uncurved space that the entire universe must be at least 250 times the radius of the observable universe. This leads to the conclusion that the unobservable universe, assuming no topological anomalies, must be at least 23 trillion light-years in diameter, containing a volume of space over 15 million times larger than what we can observe. However, there are compelling arguments suggesting the unobservable universe could be even larger. Why? The hot Big Bang may mark the beginning of the observable universe, but it does not signify the birth of space and time. Before the Big Bang, the universe underwent cosmic inflation. Rather than being filled with matter and radiation, the universe was filled with energy inherent to space itself, expanding at a constant exponential rate. This expansion occurred so rapidly that the smallest physical length scale, the Planck length, was stretched to the size of the observable universe in mere fractions of a second. Though inflation stopped in our region of the universe, three critical questions remain unanswered. 1. How large was the post-inflation region that created our hot Big Bang? 2. Is the idea of eternal inflation, where inflation continues in some regions of the universe, accurate? And 3. How long did inflation last before giving rise to the hot Big Bang? It's possible the universe where inflation occurred barely exceeds the size of the observable universe. Perhaps one day we will discover evidence of an edge to this inflation, forcing us to adjust our perception of the universe. However, it's equally possible that numerous other universes exist beyond our own, following the same physical laws and cosmic structures, raising the tantalizing possibility of complex life in other distant worlds. There must also be a finite size to the bubble where inflation ended, and an exponentially large number of such bubbles could exist within the larger inflating spacetime. Now, let's look at the most distant supernova ever spotted by astronomers, DES 16C2NM. The name comes from the fact that this supernova was first detected by the Dark Energy Survey, a research project seeking to better understand the mysterious force driving the acceleration of the universe's expansion. Supernovas are some of the largest explosions in the universe. Think of an atomic bomb but infinitely more powerful. These massive explosions are the final, valiant efforts of dying stars, usually at least 5 times larger than our own Sun. To understand how stars die, it's essential to know how they live. Massive stars burn enormous amounts of nuclear fuel at their cores, releasing immense amounts of energy and generating extreme heat. This heat creates pressure that keeps the star from collapsing under its own gravity. A balance is maintained between two opposing forces, the inward pull of gravity trying to compress the star and the outward push from the nuclear burning at the core. However, when the star's fuel runs out, it cools, pressure drops, and gravity eventually wins, causing the star to collapse in a spectacular fashion. This collapse occurs in a short period of time, sending shockwaves that cause the outer portion of the star to explode. In some cases, supernovas are also triggered when two stars collide. These cosmic events are rare, with only 2 or 3 occurring each century, making each one a special occurrence. DES 16C2NM, detected in 2016, is an exceptionally rare type of supernova. It is an extreme version of what is known as a superluminous supernova, SLSN. A team of international astronomers discovered that the explosion occurred 10.5 billion years ago, meaning the light from the explosion has been traveling toward us for over 3/4 of the universe's existence. Due to the universe's expansion, the actual location of the supernova is even farther away than that. The discovery of DES 16C2NM involved the collaboration of over 400 scientists from around the world, using 3 powerful telescopes, the Very Large Telescope, Magellan, and the Keck Observatory. The research took 5 years, with 525 nights of observation. This extreme distance provides a new insight into the nature of SLSNs, and scientists can determine the amount of metals produced by studying the ultraviolet light from the explosion. They can also calculate the temperature of the explosion, both of which are critical to understanding the causes and drivers of these massive cosmic events. While DES 16C2NM is the most distant supernova discovered, it may not hold that title for long, as astronomers continue searching for even more distant supernovas. This search is fueled by the extraordinary discovery of DES 16C2NM. You may wonder what the furthest astronomical object humans can see is. The truth is, there are objects in the universe we will never be able to see. There is a point about 16 billion light-years from Earth that marks the current cosmic event horizon of the universe. Have we reached that limit yet? Not yet. This distance is the upper limit for light reaching us, and beyond that, objects become inaccessible to our observation. If it originated at that distance today, this implies beyond 16 billion light-years, the expansion of space is faster than the speed of light itself. Obviously, the light will never reach us, as it will have to travel through a relatively expanding space. This also signifies that any event that may happen today beyond the cosmic event horizon will not be observable by us, no matter what. But we can see even further through telescopes like the JWST. The most distant galaxy ever observed is the GN Z11, located about 32 billion light-years away from Earth. Mind you, we calculate this distance taking into account the expansion of space as well. At about 46 billion light-years from Earth, we reach what's called the surface of last scattering. That's what you'll observe irrespective of the direction you look at. The surface of last scattering is like a uniform sphere of fog from which the first ever photons of cosmic microwave background radiation came after recombination and photon decoupling. Contrary to the name, it's the origin of the first ever scattering of light, but the last of what we can observe. Is this finally the edge of the universe? A yes and a no. Technically, this is the furthest point in space and the furthest in time that we can observe, which essentially forms the edge of the observable universe. What lies even beyond that is known as the opaque universe. This brings us to what is the largest object in the universe. How large is the largest thing? It's so large that it's not supposed to exist. This is because it transcends our perception of size and violates the very laws of physics. The structure is the Hercules Corona Borealis Great Wall. Cosmologists have always been baffled by the uniformity or homogeneity of the universe because the leftover heat from the Big Bang is astonishingly uniform in every direction we look. And because these early temperature fluctuations subsequently led to density fluctuations, one can also say the same thing about the matter in the universe. If the matter in the universe wasn't so smooth and uniformly distributed, large clumps would have attracted smaller chunks of matter, and the universe wouldn't have expanded but instead contracted under its own gravity. However, even though it's homogeneous on a very large scale, the universe, due to slight initial irregularities, is locally heterogeneous. The heterogeneity can be observed in dense populations of stars, galaxies, clusters, a collection of galaxies, and superclusters, a collection of clusters. The homogeneity was explained by the theory of inflation, a highly crucial aspect of the Big Bang model of the universe. This model is currently believed to be the most convincing explanation of the birth of our universe. However, the Hercules Corona Borealis Great Wall is a supercluster that represents such an immense irregularity or non-uniformity that it defies the laws of inflation. The supercluster is so humongous that it exceeds the maximum structural size allowed by the inflationary model of the universe. The Hercules Corona Borealis Great Wall was discovered in 2013 by a team of astronomers led by I. Horvath, J. Heiler, and Z. Bolai while looking for gamma-ray bursts, GRBs. For this reason, the structure is often called the Great GRB Wall. Gamma rays are the most powerful type of radiation in the entire electromagnetic spectrum. Such super high-frequency radiation emanates only in a handful of stellar events, such as supernovae, the explosive death of a star, collisions of neutron stars, or matter spun around violently by a black hole. The energy released during a supernova is so colossal that the Sun cannot produce the same amount during its entire lifetime. Astronomers study these bursts because they enable us to locate massive structures in the universe. Massive stars can only form around a dense surplus of mass because that's what they feed on, along with planetary systems.